So when we take a look at this problem, the first thing that we need to figure out is what does that molecule look like? And so is that a hexane? That's 6 carbons, and we need a bromine at position 2. Now we just need to make sure that's also R. 1, 2, and 3. That is an R configuration. So that's our starting material. That's what it looks like. The next thing that we need to do is step 1 is, do we have a good leaving group? Yes, we do have a good leaving group, so that's good. What's another thing that we need to have? Is that leaving group attached to a sp3 hybridized carbon? Yep, that checks out. So after that looks good, then we there's like a step 3. I want to look at the degree, and that would be a secondary alkyl halide. And since that's secondary alkyl halide, that means all 4 factors, not 4 factors, 4 mechanisms are on the table. And so now we just have to go through the factors here to kind of get an idea of what kind of mechanism is possible. So we first see in the factors is the strength. Is the attacking species strong or weak? When we zoom in on that guy, we see that it looks like this. And then you have the positive potassium. So that species is a strong attacking species. And so strong attacking species favors SN2 and E2. And it is a strong base and a strong nucleophile due to its size right there. It's not sterically bulky. The concentration, it doesn't tell us that it's dilute, so we assume that it's SN2 and E2. It is a good leaving group, so those tend to favor the kinetics of SN1 and E1 more so than SN2 and E2. The solvent is DMSO, which is a polar A product solvent. And there we go, we tallied it up. So we have a tie right there. And so we will use another factor to break that tie by noticing that we have heat added. So that would make the E2 mechanism the preferred mechanism. And then from there, we have to analyze our starting material. Let's go right here. There's our starting material. We said E2. And so E2 mechanism here, and the base was ethoxide, I believe. And so we have options here. Okay. We can grab that proton, or we could grab one of these protons. But remember, we want this anti-periplanar. And since there are 2 hydrogens here, this is an example of a stereoselective. Which one are we going to grab? H1 or H2? Because what can happen is you can get 2 possible products. You could get this product right here. You could get this product here. I said 2, but there's actually potential of 3. And then we could get this product here, right? 1, 2, 3, 4, 5, 6. So we have the trans product, we have the cis product, and then we have this mono-substituted product. And the other 2 are di-substituted. Now so out of the gate, after we predict those products, we could all say that that guy's not going to be the major product because it's only mono-substituted. And because these 2 protons right here would give us a di-substitute product. So based off of thermodynamics, we would expect the di-substituted alkenes to be the major products. Now between the trans and the cis, which one is going to be preferred? That is going to be the trans product right there because we have options. H2 is going to give us the trans product, whereas H1 will give us the cis product. And so that leaves us with an answer choice of D right there. Okay, let's go here. Let's go through the process. The same process every time. Step 1, do we have a good leaving group? Yes. Step 2, is that an sp3 hybridized carbon that the group is attached to? Yes, it is. Step 3, what is the degree of that alkyl halide? That would be a secondary alkyl halide. So all 4 possible mechanisms are on the table. So if we zoom out a little bit, strength. We look at that species right there and we notice that CH3, CO minus, and there's the spectator ion. That right there is terbutoxide. So that is a strong attacking species. So you would check those 2 right there, but we notice that it is a terbutoxide, which is a sterically hindered base. So no substitutions. That's not going to be possible. Then the concentration favors SN2 and E2. Nothing's there about dilution. The leaving group would promote SN1 and E1. DMF is another polar aprotic solvent, so SN2 and E2. And now we have a clear winner that this mechanism would have to proceed via E2 mechanism. So then that leaves us, when we look at that starting material, we have a couple hydrogens that we could abstract. We could abstract that one, we'll call it H1, or we could abstract not H1, I take that back. There is, well, let's put that hydrogen back actually. There is H1, that is true, and then there's H2 over there, and then H3. There's only going to actually be one possible product in this particular case because we identified that we are going to do an E2 mechanism. So that means we have to abstract the proton that's going to be anti-periplanar. H1 is on the same side as the leaving group. You can see that they're both dashes. So that's syn periplanar. That is not an option. They need to be anti. H3 is also syn periplanar. Can't use that one. But it is H2 because they're on opposite sides of the ring, or said another way, they are anti-periplanar. And so mechanistically, our terbutoxide, which I'm just going to represent as just a B for base, just to keep things simple, but that bulky base now is going to come in and grab H2, put the electrons between the alpha and the beta carbons, kicking off the bromine. So let's clean that up. Kicking off the bromine like that. So that's going to leave us with only one possible product, and that would give us E as the only product in that reaction. So now we come back to what looks like a similar problem, but look at the difference. The leaving group is on a dash versus a wedge. So steps 1 through 3 all check out. It's the same problem except for the stereochemistry of that Stereocenter right here. So if we go and look at the strength thing is also going to be exactly the same. Or everything on this this table right here is going to be the exact same thing for this one down here. So we don't need to go through and redo it. So we know that it's going to be an E2 favored mechanism. So if we go through and analyze it the same way that we did the previous one, we have these dashed hydrogens right here. H1, H2, and H3. The base, which is the same as the previous, which one is it going to abstract? It could abstract this one. And if it abstracts H1, then you are going to get which product here? Trying to see the answer choices. It would have to be D if you abstracted H1. But that base could also have abstracted H3. Let me finish the red mechanism here. So both are plausible. Now, and the green arrows would have given us this as our product. So we have issues going on here. Okay. Now, some might argue that answer D would be the major product because it's the most thermodynamic product, because that is going to be a tri-substituted species, which is accurate. That is a tri-substituted species, and the green one is a di-substituted alkene. From a thermodynamic perspective, you're right, that the red, or answer D, would be more thermodynamically stable. However, when you consider the base, it is a sterically hindered base. And so that's going to promote a selection for H3, because that's going to be less sterically difficult to get to. So H1 is more sterically hindered than H3. So kinetically, what is going to form fastest would be abstracting off proton 3. So the major product here would be E. That would be the correct answer because we have to factor in steric effects. Okay. So it looks like now in this particular problem, same starting material as in question 3, but now what has changed? The only thing that has changed is the attacking species. Is that attacking species a strong attacking species? Yes, it is. That can behave as a nucleophile and a base. So what we're going to have is for problem 4, it's going to look exactly like this one, except we are going to have this check mark right there. And so now we're going to have a two-way tie. And so how do we break the tie between SN2 and E2? Well, we go and we look a little more carefully, and we see that we have heat being added. So that is going to force this reaction to a E2 mechanism. When we go and draw out our hydrogens again, H2, H1, now when the base, which I'm just going to represent with the letter B, that can abstract H1 like this, and it could come in and grab H3 like so. And that would give us the possible products of D or E. But the base here is not sterically hindering. It can go and approach H1 and H3 with, relatively the same ability. But since the base can go for both, why would it not just give you the more bang for your buck and give you the more thermodynamically favorable product? So it's going to favor H1. That's the proton that the base is going to prefer to go to. And so that would give us what as the correct answer. So for problem 4, D would be the correct answer. And then the last question right here. Let's go through the process. Step 1, we have a good leaving group. Step 2, that is sp2. Sorry, that would be sp3. And then step 3, that is a secondary. So with that information, we know we can do this reaction, and all 4 mechanisms are on the table. So now we just go back to our little table here. The strength of the attacking species. When we look at the strength of the attacking species right there, you can see that the oxygen has 2 lone pairs and it's neutral. So because it's neutral, that's going to favor SN1 and E1. When we look at the concentration, there's nothing talking about it being dilute. So we assume that it's concentrated. So that favors SN2 and E2. The leaving group ability, that is a wonderful leaving group, and that's going to promote a faster reaction for SN1 and E1. The solvent, this might have tripped some people up. The solvent is also the attacking species in this particular case. That is ethanol, which is a liquid. And so ethanol, what type of solvent is ethanol? When you take a look at it, you zoom in and you notice we have a hydrogen attached to an oxygen atom. That can then proceed to do hydrogen bonding with itself. So that would make that a polar protic solvent. And polar protic solvents are going to favor SN1 and E1. So now we tally this all up, and we see that we have a two-way tie between SN1 and E1. So now we have to go and take a look. Is heat mentioned in any of these? And you'll see that heat is not mentioned. So the winner is going to be our SN1 mechanism. So when we take a look at our species here, and we go through the mechanism, I hope you guys are going through the mechanism, because it's going to help you in so many ways, more so than you really realize. So this, we predicted this to be an SN1, so that means the leaving group has to leave first. When the leaving group leaves, then we are going to generate a secondary carbocation. And what are we supposed to do whenever we have a secondary carbocation? We look for rearrangements. And so what's going to rearrange is a methyl group. That's going to shift over. We do that. Let's go like this. So that's going to give us a methyl group there, and then that. So now we've gone from a secondary carbocation to a tertiary carbocation. Okay, and now that we have our carbocation, we can now use our, what's our attacking species? Ethanol. Like this. And then that's going to come in and attack. It can attack from the front face or the back face. Both are options. And then we have O. That oxygen atom right here has formed a bond with the carbocation. And that's what I'm drawing right here, is that oxygen forming a bond with that carbon. Now, looking at the red arrows, did the hydrogen fall off? No. Did any of that fall off? No. So it comes along for the ride. We still have CH2. Well, you know, I'm going to draw it like this with skeletal structures just to keep it nicer. Okay. But the hydrogen's still there, so we have to keep it there. So now we have a protonated alcohol. And now the last step, we would take another molecule of ethanol to act as the base this time to do a proton transfer to generate our product like this. And then plus OH2, there's our protonated ethanol. from the proton transfer step. And so that should give us what as the answer choice? That one. So G would be the correct answer. Okay, as always, if you have any questions or concerns, feel free to ask and get help.